130 million years ago, something strange moved through an ancient sea. It was not the strangest thing alive in that ocean. The early Cretaceous seas were full of extraordinary creatures, long-necked predators, armored fish, animals that had no living equivalent today. But this particular animal had a body that didn't quite make sense, even by the standards of a world already full of impossible things. This one was unusual. It was roughly 7 meters long, about 23 feet, with four broad paddles and a neck that may have contained up to 51 vertebrae. A neck, in other words, nearly as long as the rest of its body. But it was the face that stopped scientists in their tracks. It was too short, almost blunt. The back of the skull was enlarged out of all proportion to the front. The eye sockets were enormous, far larger than any obvious need seemed to demand. The jaw was narrow, almost delicate, while the chest was wide and reinforced with unusually dense, heavy bones. The animal looked, in some ways, like a creature that had simply refused to finish growing up. Certain parts of its skeleton had the proportions more commonly seen in juveniles, preserved permanently into adulthood. Scientists named it Abyssosaurus, the abyss lizard. The name was a theory as much as a title. Some researchers believed those enormous eyes, that heavy reinforced body, that strange blunted face, all of it pointed to a life spent in deeper, darker water than most of its relatives ever entered, but proving it was another matter entirely. And the mystery didn't end there. When the animal was first described, scientists believed most of its skull was missing. Years later, they discovered that the skull had been there all along, sitting among the already collected remains, overlooked. Then its place in the family tree was questioned, then reconsidered, then questioned again. More than a decade after its discovery, Abyssosaurus still refuses to be fully explained. There is only one skeleton, one deeply unusual animal, and a series of questions written into its bones that science has not yet finished answering. This is the story of that skeleton and what it might tell us about a part of the prehistoric ocean that almost nothing else dared to enter. If this is the kind of mystery you want to go deeper into, please take a moment to like this video and subscribe. It genuinely helps bring more stories like this one to more people. Let's go back to that ancient sea. 130 million years ago, the continents had only begun their slow drift toward the shapes we recognize today. Pangaea had broken apart, but the pieces still remembered their closeness. Laurasia and Gondwana, the supercontinents that would eventually become our modern world, remained locked in their own slow separation, and in the spaces between them ran a seaway of extraordinary scale and warmth. The Tethys Sea stretched across the equatorial band of Earth like a ribbon of life. It was not one ocean, but a collection of them, a great tropical waterway that divided the northern from the southern continents, warm from pole to nearest pole, teeming with forms of existence that had no modern parallel. Nowhere was this seaway more intimate than in what would become the Chuvash Republic of Russia, where an inland arm had flooded vast stretches of what was then European landscape. This was not the open ocean, it was an epicontinental sea, a massive inland lake-sea hybrid, and it held a completeness of life that only a mature ecosystem could contain. The climate of that age was different from the world we inhabit. Carbon dioxide hung thicker in the atmosphere. Ice had retreated from the poles entirely. There were no polar ice caps, no permanent snow anywhere on the planet. Temperatures ran warmer overall, perhaps 8 to 9 degrees Fahrenheit higher than present day, and the warmth was not distributed evenly. The tropics were hot, often oppressively so, and the oceans themselves absorbed and held that heat with an efficiency that modern seas cannot match. Sea levels had risen, perhaps 260 to 330 feet higher than they stand now, drowning coastlines and filling the low places where continents met the margins of deeper water. The sea that held Abyssosaurus had been running this way for a long time. It had been running for 65 million years already, which meant the Mesozoic marine world was not young or experimental. It was mature, it was complex, it was layered in ways that only deep time can produce. Species had appeared and disappeared. Predators had evolved to hunt in every depth. Prey had evolved to hide in every crevice. The ecosystem had refined itself through millions of generations until it functioned with the precision of an instrument tuned so finely that each string sounded true. Ammonites drifted through the water column, their spiral shells catching what light penetrated from above. Belemnites, their squid-like cousins, hunted in midwater. Early sharks, still diversifying, still experimenting with body plans, moved through their own ecological lanes. Ichthyosaurs, with their dolphin bodies, cut through the shallows and mid-depths in pursuit of fish. Pliosaurs, massive and muscled, occupied the apex tier of that upper realm. At every depth, something hunted. At every depth, something fled. This was the world that existed before Abyssosaurus descended. This was the abundance, and the abundance was real. Yet, even in a sea this full, a place remained empty, a depth remained uncontested. A way of life awaited an animal brave enough to abandon the light entirely and sink into the realm where no current carried warmth and no sunlight had ever reached the water below. Before dinosaurs walked the continents, before the first of the long necked giants emerged from egg into air, a different branch of the reptile family had already solved the problem of the sea. These were the Sauropterygians, a lineage entirely separate from dinosaurs, creatures that had returned to water with such commitment that their land-dwelling ancestors had faded into deep time. They appeared during the Triassic period, approximately 210 million years ago, and they would not relinquish their dominance until the very extinction that killed the dinosaurs 66 million years ago. For 144 million years, they owned the oceans. Evolution invented them twice, not in the sense of separate creations, but in the sense of repeating solutions across different epochs and different seas. Some became long-necked hunters with small heads and elongated bodies, creatures built like living fishhooks with flippers. Others grew massive jaws and powerful frames, becoming apex predators of extraordinary scale and strength. These were not two species that persisted unchanged. They were entire families of body plans that evolution reinvented across lineages, across geological time, across oceans separated by continents. Long-necked forms emerged in the Jurassic, vanished, and emerged again in the Cretaceous. Short-necked forms appeared in one era, dominated, faded, and their ecological role was seized by new short-necked lineages in a later age. Convergence spiraled upon itself, creating solutions so effective that nature found no reason to abandon them. By the time the early Cretaceous arrived, plesiosaurs had colonized the entire planet. They hunted in polar waters where the sun barely rose above the horizon. They patrolled tropical shallows where the heat pressed down from above. They ranged through open ocean far from any coast, and they carved territories in the narrow seas that cut between continents. Everywhere water existed, plesiosaurs had learned to swim through it. The way they moved through that water was unlike anything evolution has produced since. Four broad paddles worked in concert, each one an independent flipper capable of its own precise movement. Researchers have argued for decades about the exact mechanics of their locomotion, comparing them to penguins that porpoise through air that is water, to sea turtles that fly with their flippers, to nothing in the modern ocean because nothing quite duplicates what plesiosaurs did. The four flippers did not simply push water backward like a fishtail. They worked together in a coordinated rhythm that generated forward movement through a kind of underwater flight, each paddle a wing. The mechanics remain partially mysterious because no living animal performs exactly the same action. They were air breathers, which meant a fundamental constraint: they could never fully leave the surface world. Lungs tied them to the air above as surely as chains would have. They could not lay eggs on sand. They could not haul themselves onto rocks to rest. Instead, they had evolved to give birth in open water, delivering live young into an ocean that offered no refuge, no nest, no dry place. Their entire existence was aquatic. Their entire reproduction happened at sea. They had crossed a threshold from which there was no return to land, and they had crossed it completely. Among the plesiosaur families that thrived across these immense spans of time, one lineage carved out a particular niche, neither flashy nor massive, but persistent. The Cryptoclididae emerged during the Middle Jurassic, approximately 170 million years ago, and they would endure through the Early Cretaceous, a tenure of roughly 40 million years. In geological time, this is not insignificant. It is a sentence written in stone, a proof of adaptive success, a family that found something that worked and held on to it through the rise and fall of other dynasties. Cryptoclidids were moderate in size, typically ranging from 10 to 20 feet in length, which made them neither the smallest nor the largest plesiosaurs in their waters. They possessed medium-length necks, proportioned differently from their extreme-necked cousins, and their flippers were unusually large relative to body size, built for precision rather than power. These were not the apex predators that commanded fear through sheer mass. They were something else entirely. Specialists, hunters calibrated for a particular kind of prey and a particular way of hunting. The teeth were small and pointed, designed for grasping rather than crushing. The jaws were not built for tearing flesh from massive prey, but for holding struggling forms of squid and crustacean long enough to swallow them whole. The roster of known genera reads like a catalog of understated efficiency. Cryptocletus, from which the family takes its name; Columbosaurus, another fixture of Jurassic seas; Chimerosaurus, persisting into later periods; Murrayanosaurus, ranging through different oceans. Each name represents an animal that had solved the problem of eating well in waters crowded with competitors. They fed on fish, on squid, on crustaceans that could not be chased but only ambushed. They hunted in the middle depths and shallows, territories already occupied by other predators, yet they held their ground by being excellent at one specific thing rather than adequate at many. By the time the Cretaceous arrived, the family was already showing signs of contraction. The leptocleidids were rising, a competing plesiosaur family that would come to dominate certain regions. The elasmosaurids, with their extreme necks and specialized feeding strategies, were diversifying rapidly, spreading into ecological niches that cryptoclidids had once held without contest. The world was changing in ways that favored other solutions, other body plans, other ways of being a long-necked marine reptile. Cryptoclidids were not disappearing suddenly, but they were losing ground year by year, generation by generation. Abyssosaurus appeared in this context at the end of a lineage that was already fading. It was not the first member of its family, nor was it a survivor clinging to an ancient design. Rather, it represented something unprecedented, a cryptoclidid that had abandoned the moderate depths where its relatives hunted and had instead descended into territories no other member of the family had ever explored. It had taken the ancestral toolkit of Cryptoclididae and reinvented it entirely for a new purpose. The moderate flippers that earlier cryptoclinids had used for precision maneuvering in midwater became instruments of controlled descent. The medium-length neck, adequate for sweeping through schools of fish, transformed into a reaching mechanism for something entirely different. In doing so, Abyssosaurus stepped outside the family's proven strategy. It did not compete with the rising elasmosaurids or the diversifying leptocleidids. It simply left the competition behind, sinking beneath it, into the realm where no plesiosaur had ventured before. A plesiosaur should float. This is what evolution had prepared its lineage for across 144 million years. Light bones, air-filled cavities, the buoyancy of a reptile built to breathe air. All of these were advantages in a creature committed to the surface world. Staying near the light cost nothing. The surface was home, and home was free. Abyssosaurus chose differently. Every bone in its skeleton told the story of that choice, written in density and weight. The gastralia, the abdominal ribs that cage the organs, were thickened far beyond what its relatives possessed. The flippers, those four paddles that should have been light and mobile, carried bones so dense that it seemed to reject the very concept of buoyancy. This thickening, this pachyostosis, was not a disease or a deformity. It was a strategy. It was adaptation written into the skeleton as deliberately as words written into stone. Pachyostosis means exactly this: an increase in bone density so severe that the air spaces within bone, the chambers that would normally provide lift, were compressed and reduced. The bone became harder, denser, less forgiving. It weighed more in water. It resisted floating with every fiber of its structure. This transformation came at a cost that cannot be overstated. Building such bones required energy. Maintaining them required constant metabolic investment. Carrying them through water required effort with every movement. There was no advantage to this density unless density itself was the point. The only reason an animal pays such a price is if staying near the surface has become a liability rather than an asset. If the goal shifts from floating effortlessly to sinking deliberately, then every thickened bone becomes an investment in a different kind of survival. Abyssosaurus had made that shift. It had decided that the deep was where it belonged. The proportions of its flippers reinforced this commitment in a way that was unusual among plesiosaurs. The hind flippers were significantly longer than the front ones, creating an imbalance that, combined with the dense skeleton, would have produced a particular effect in water. The animal would not float horizontally like its relatives. Instead, it would tilt, nose up and tail down, hovering at an angle to the seafloor below. This was not a flaw in its design. This was the design itself, perfected through generations of descent into the depths. A scientist named Alexander Berezin would later reconstruct the hunting posture this created: an animal suspended diagonally above the seafloor, patient and angled, its small skull directed downward toward the sediment where prey lived. The long neck would allow it to reach, to probe, to investigate the spaces between rocks and shells where cephalopods curled and crustaceans hid. The body, weighted and positioned, would hang above like a hovering bird, but a bird hunting in darkness rather than air, in water rather than wind, in a realm that demanded a completely different kind of patience. This was not a creature that had adapted to depth by accident or circumstance. This was a creature that had engineered itself for the abyss with purposeful, deliberate transformation. Every dense bone was a choice. Every elongated hind flipper was an argument for descent. The decision to sink was written across its entire form. For 7 years, the skull of Abyssosaurus, sat in a museum collection, invisible among the scattered remains of the skeleton it had once animated. It was there all along, pressed into the sediment near the shoulder girdle, mixed among bones that seemed ordinary, unremarkable. No one recognized it. No one understood what they were looking at until 2018, when Alexander Berezin returned to the specimen and truly saw it for the first time. When he did, the skull confirmed everything the body had already whispered. It was small, triangular, compact in a way that seemed almost incomplete, as though the animal's head had refused to finish developing into the shapes typical of its family. There was no long snout built for speed striking, no sweeping jaw like the massive plesiosaurids carried, no delicate crocodilian profile. Instead, the skull presented itself as a precise instrument, short and blunt, designed for something far more specific than general predation. The eye sockets dominated the small skull, enlarged far beyond what an adult animal of its size should have possessed. This was not normal. In most plesiosaurs, the orbits were proportioned to the head, refined through growth as the skeleton matured. In Abyssosaurus, they remained oversized, retaining the proportions of a juvenile animal, but maintained into full adulthood. This was not a failure of development. This was a feature, preserved and functional, calibrated for a particular kind of vision. Large eye sockets meant large eyes, and large eyes in the context of the depths meant something very specific: the ability to gather every available photon in an environment where photons were vanishingly rare. The bathyal zone, where this creature descended, receives no sunlight. Not a dim twilight, not a filtered glow, but absolute darkness except for the bioluminescence that organisms produce in order to communicate, to hunt, to navigate through black water. Eyes this large would collect every available spark of that biological light, would process starved photons into images, would allow an animal to hunt by capturing the faintest flash of prey. The teeth reinforced this picture of specialized hunting. They were conical and slightly curved, not the crushing teeth of a shell breaker or the tearing edges of a flesh ripper. They were grasping teeth, designed to hold soft bodies, cephalopods, and crustaceans that could not be chased through open water but had to be ambushed in darkness, seized before they could flee into crevices or release ink into water already black as pitch. A narrow jaw meant the mouth could not open very wide, which meant the prey had to be small, had to be grabbed whole, had to be held firmly until swallowed. Berezin's interpretation of the skull was not speculation overlaid onto bone structure. It was argument written in geometry, in proportions, in the physical facts of how this animal was built. The enlarged orbits were direct evidence of deep diving. The short triangular profile was direct evidence of a hunting strategy that had nothing to do with speed or power. The narrow jaw with its precise teeth was direct evidence of a life spent pursuing prey that lived in absolute darkness. The skull was a record, and the record was unambiguous. This animal had been built for the abyss from birth. The bathyal zone begins where sunlight gives up entirely. At 1,000 feet below the surface, the pressure has become 100 times stronger than what a body feels in air. At 13,000 feet, it reaches 400 times. The temperature hovers just above freezing, somewhere around 35 to 38 degrees Fahrenheit, and nothing in this realm has ever known warmth the way creatures on the surface do. Sunlight has not reached these depths for millions of years. It will not reach them for millions more. Yet here, in absolute darkness and crushing weight, life persists in forms that adapted long ago to an environment that asks everything of whatever enters it. This was where Abyssosaurus went to hunt. The prey existed here in extraordinary abundance, largely uncontested by surface predators that lacked the commitment to descend so far. Cephalopods drifted through the water, their soft bodies adapted to low pressure, their intelligence available for both ambush and evasion. Crustaceans crawled along the seafloor, their armor protecting them from the immense weight of water above. These creatures had learned to survive in darkness. Abyssosaurus had learned to hunt them there. The strategy required no speed, no burst of predatory violence. It required instead the opposite: hover above the sediment on angled flippers, sense the movement of prey through the water, the vibrations in pressure, the faint bioluminescent signals, and then strike with the short, precise jaw, holding and swallowing in one committed motion. But Abyssosaurus was not a fish. It did not have gills that could extract oxygen from water. It had lungs, the inheritance of its reptilian ancestry, and lungs demanded air. This created a constraint that shaped every moment of its existence. It dove into the depths, hunted in the darkness, fed on prey that belonged to that realm, and then it had to ascend. Hundreds of feet, possibly thousands, climbing through water that grew progressively warmer and less dense, returning to a surface world that had become foreign to it. The surface was necessity only, a place to gulp air before the next descent began. This cycle of ascent and descent happened repeatedly across the span of Abyssosaurus's life. Each journey down was an investment in hunting. Each journey up was a debt to physiology. Berezin proposed that Abyssosaurus had evolved an adaptation to manage this burden, a network of capillaries in its body that resembled the retia mirabilia found in modern sperm whales. These vessels, literally wonderful nets of blood vessels, served to regulate oxygen distribution throughout the body during deep dives, allowing the heart to slow and the metabolism to conserve, extending the time an air breather could remain submerged before needing to return. The mechanism was not perfect. It was simply as good as evolution could make it, allowing an animal built for air to survive in depths where air was an impossibility. The pattern repeated across decades, across a life measured in slow metabolisms and patient hunts. Every breath Abyssosaurus took at the surface was a return to a world it did not belong to anymore. Every dive was a return home. Sperm whales are the deepest diving mammals alive. They descend to depths exceeding 6,500 feet, holding their breath for up to 90 minutes while hunting giant squid in water so dark that nothing else penetrates it. They manage this through an organ unique to their kind, the spermaceti, a chamber of waxy tissue in their massive head that allows them to adjust their buoyancy with precision, becoming neutrally buoyant at depth so they can hover and hunt without fighting against the water's pressure. They descend head down at an angle, hunt in that crushing darkness using echolocation to find prey, and then climb back to the surface for air. The entire strategy is built around a single fact: they need to breathe, and breathing means returning to a world far above. Sperm whales evolved approximately 23 million years ago. They are relatively young in evolutionary terms, a solution to deep water hunting that arrived late in the story of mammals. Abyssosaurus lived 130 million years ago during the early Cretaceous, long before whales existed at all, long before mammals themselves had diversified into their modern forms. Between these two creatures lies a gap of 107 million years. They never shared an ocean. They belonged to completely different geological epochs, different continents, different planetary configurations. Yet they arrived at the same answer. Both animals are air breathers. Both carry bodies too dense and complex to survive by floating near the surface. Both descended into depths that most of their relatives refused to enter. Both hunted in absolute darkness, using whatever senses remained useful in that lightless realm. Both had to return to the surface to breathe, which meant both endured a cycle of descent and ascent, of belonging to two worlds that rejected them equally. The physical solution they developed was nearly identical. Weight the body, descend at an angle, hunt with patience rather than speed, ascend to gulp air before the next dive begins. This convergence reaches beyond simple body shape or isolated behavioral adaptation. It encompasses an entire way of being, a complete rethinking of what it means to be an air-breathing predator. Most air breathers avoid the deep because the deep is hostile to their kind. Sperm whales and Abyssosaurus did not avoid it. They engineered themselves for it, paying enormous biological costs to access a realm that offered one advantage: prey that few other predators had learned to pursue. Convergent evolution is the phenomenon where unrelated lineages independently develop similar solutions to similar problems. Fish evolved fins, birds evolved wings, bats evolved wings of a different design. These are striking examples, but they involve structures that are easily reinvented, body plans that multiple paths can reach. The convergence between Abyssosaurus and sperm whales is more extraordinary because it is more specific. This is not merely two animals developing similar shapes. This is two completely unrelated lineages, separated by over 100 million years, solving an identical problem in an identical way. Evolution does not repeat itself by accident. It repeats itself when the problem admits of very few optimal solutions. The deep sea is such a problem. Something about its conditions, its pressures, its darkness, its scarcity of prey shapes the answer it elicits from anything that attempts to enter it. The answer comes out the same every time. The skeleton of Abyssosaurus tells a story that most adult skeletons do not. In related plesiosaurs, the body undergoes transformation as it ages. The skull changes shape, becoming more angular, more refined. The vertebrae differentiate, each one developing its own character. The proportions shift, the proportions of a juvenile giving way to the proportions of a mature animal. But in Abyssosaurus, this transformation never occurred. The adult animal retained the skull of a young one. Its eye sockets remained oversized, its jaw remained narrow and triangular, its vertebrae maintained the homogeneous structure of early development. The wide chest and shoulders that appear in juvenile plesiosaurs stayed with Abyssosaurus into maturity. This animal was scaled up to adult size, but its skeleton had refused to grow old. This phenomenon has a name: paedomorphosis. It is not a disease or a sign of arrested development. It is an evolutionary choice, a fundamental alteration of how time moves through the body during development. Rather than following the typical schedule where youth transforms into maturity, the organism slows or stops certain aspects of that transformation, retaining juvenile characteristics indefinitely. This is not unique to Abyssosaurus. Axolotls, the aquatic salamanders that never metamorphose, exhibit paedomorphosis. Certain deep-sea fish retain larval traits throughout their lives. Some whale lineages show evidence of this same pattern, keeping features that their ancestors shed upon reaching adulthood. The deep sea appears to select for this strategy repeatedly, across unrelated lineages and different evolutionary pathways. Alexander Berezin proposed an explanation that reframes the concept entirely. In harsh, cold, high-pressure environments, The conditions that reward rapid growth and rapid reproduction do not exist. Food is scarce, reproduction is infrequent, space is abundant. The pressure to mature quickly and breed early vanishes. Instead, evolution favors organisms that grow slowly, reproduce rarely, and live for decades or longer. In such a context, retaining juvenile anatomy becomes advantageous. Smaller bodies need less food. Conservative metabolisms waste no energy on aggressive growth. Patience becomes the primary survival strategy. Abyssosaurus embodied this entirely. Its small, triangular skull meant a small mouth and targeted feeding rather than bulk consumption. Its oversized eyes, inherited from youth and never downscaled, suggested a life that would span many years of careful hunting in darkness. Its vertebrae, never fully differentiated, indicated a reduced speed of life throughout its existence. Berezin calculated that Abyssosaurus may have lived for decades, possibly longer than most of its relatives in the warmer, brighter shallows above. It grew slowly. It descended patiently. It returned to the surface on a rhythm that no living creature could have observed, on a schedule known only to itself. This interpretation transforms pedomorphosis from a developmental curiosity into an adaptive strategy. The deep does not reward becoming adult in the way that surface life does. It does not favor the aggressive development that produces large, fast-breeding animals. The deep rewards the opposite, an organism that keeps the proportions of youth, the conservative metabolism of young life, the patience of an animal that understands scarcity as the natural state. Abyssosaurus never became old because the environment never made adulthood profitable. It remained perpetually young, perpetually careful, perpetually adapted to a life that demanded everything and gave very little in return. Cold descends with depth. The warm tethys that Abyssosaurus briefly touched at the surface, where it gulped air into reptilian lungs, gave way to progressively colder water as the creature sank. Not the crushing cold of polar seas, not the near-lethal freeze of Arctic depths, but a sustained chill that permeated everything below. A temperature that hovered around 35 to 38 degrees Fahrenheit and never varied. This cold had consequences that reached into every aspect of the animal's physiology. Cold water carries more dissolved oxygen than warm water does. The paradox of the deep is that darkness and cold together create an environment that seems hostile, but which actually offers one subtle advantage. Oxygen remains available in quantities that surface dwellers cannot match. The bathyal zone, despite its crushing pressure and absolute darkness, maintains a kind of life that is continuous, if sparse. This life moves differently, operates on different timescales, follows patterns that evolved long ago and have persisted unchanged. The creatures that thrive here have adapted to cold by slowing, by metabolizing less, by making every movement count. Abyssosaurus's dense bones served multiple purposes. Yes, they facilitated descent, making the animal heavier in water, counteracting buoyancy that would otherwise pull it toward the surface. But the thickened skeleton also reflected something deeper, a body adapted to survive in cold. Denser tissues generate and retain heat more efficiently. Reduced internal gas volumes meant fewer chambers that could compress dangerously under pressure, fewer spaces that could rupture or collapse. The entire skeletal architecture represented a physiology calibrated to function in an environment where most bodies would fail. The way Abyssosaurus moved through water reinforced this picture of cold adaptation. Four flippers working in concert, generating momentum through sustained effort rather than explosive speed, suggested an animal built for cruising rather than chasing. The hind flippers, longer than the front ones, drove propulsion forward in a rhythm suited to patience. This was not the locomotion of a predator that sprints and strikes. This was the movement of a creature that had restructured its relationship with energy itself, spending it carefully, investing every movement in a hunt that might take hours or days to complete. The world that produced Abyssosaurus had itself been cooling. The Hauterivian stage of the early Cretaceous, approximately 132 to 125 million years ago, had followed the Weissert event, a global cooling episode that dropped sea surface temperatures by 3 to 4 degrees Fahrenheit. This cooling was brief in geological terms, but it reshaped the ecosystems that responded to it. Abyssosaurus emerged on the other side of that temperature shift, possibly bearing its mark in the very structure of its bones, in the efficiency of its metabolism, in the patience that defined its approach to hunting. The animal that descended into darkness carried with it an inheritance of adaptation to cold. Denser, slower, more conservative in every aspect, it had evolved to thrive in conditions that most of its relatives would find intolerable. The deep was not refuge from cold. The deep embodied cold in its purest form. Abyssosaurus had not fled into the abyss to escape. It had descended because everything about its body and its life had prepared it to live there. The water above Abyssosaurus teemed with life in ways that the depths below did not. While the plesiosaur hung in darkness, angled and patient, an entire layered world operated in the sunlit and twilight zones overhead, a complete ecosystem with predators at every accessible depth and prey distributed across the water column in patterns shaped by millions of years of coevolution. This upper realm was crowded in the way that the depths were sparse. Luscon idalensis hunted in those warmer waters, a plesiosaur recently described from the same Russian seas and the same geological moment, approximately 130 million years ago. Its skull stretched to nearly 5 feet in length, built for the kind of apex predation that required speed and power. Where Abyssosaurus had refined itself for ambush in darkness, Luscon represented the opposite strategy: a massive head, powerful jaws, a body built to chase and capture prey in open water where speed conferred advantage. Both animals occupied the same sea, yet their niches could not have been more different. Ophthalmosaurid ichthyosaurs patrolled the mid-water column with the streamlined efficiency of modern dolphins. Platypterygus and its relatives hunted fish in the sunlit zones, their large eyes scanning for movement, their torpedo bodies capable of the burst acceleration that prey required them to match. They had evolved for speed in a way that Abyssosaurus had not. They lived in a different temporal rhythm, operating on time frames measured in seconds and minutes rather than hours. The cephalopods drifted and hunted throughout the water column, filling niches that required intelligence and flexibility. Ammonites, the spiral-shelled squid-like creatures, existed in extraordinary diversity. Symbirskites, with its distinctive ribbing, Spitonoceras, with its fine ornamentation, Endemoceras, with its regional specificity. Each species occupied its own depth zone, its own hunting ground, its own ecological role. These were the creatures that Abyssosaurus may have pursued in the deep. In the shallows and mid-depths, they served as prey for the ichthyosaurs and smaller pliosaurs. Belemnites, the torpedo-shaped squid relatives, inhabited the entire water column simultaneously, their abundance providing a consistent food source across multiple depths and predator types. Pliosaurids still dominated the open water, patrolling territories that would have made the smaller Abyssosaurus seem insignificant. Early sharks moved through their own ecological lanes, diversifying, experimenting with body plans and hunting strategies, beginning the process that would eventually make them the dominant predators of the modern ocean. Every depth hosted hunters. Every level of the water column hosted hunted. Abyssosaurus existed within this ecosystem, but not as a part of the competitive hierarchy that structured the world above. The deep was the one domain where no other plesiosaur had learned to hunt effectively, where no ichthyosaur had committed to surviving, where the scattered cephalopods and crustaceans had few predators to fear. By sinking, Abyssosaurus had not conquered the sea that held it. Instead, it had found the one empty space in an otherwise packed world. The abyss was its answer to an ocean too crowded with hunters for any new strategy to thrive. In the darkness below, where pressure and cold and eternal night kept competitors at bay, Abyssosaurus had claimed something that no relative of its kind had ever claimed before, a kingdom of its own. Plesiosaurs belonged entirely to the sea. Their flippers, evolved from the limbs of land-dwelling ancestors, had become instruments of swimming rather than walking. Their bodies had committed so completely to aquatic life that returning to shore would have meant death. The weight of their own skeleton would have crushed them without the buoyancy of water to support it. This posed a biological puzzle that troubled paleontologists for decades. If plesiosaurs could not come ashore, how did they reproduce? Where would eggs be laid if no beaches were available, if every moment of existence was spent in open water? The answer arrived in 2011 from a fossil discovered in Kansas. A polycotylus, a smaller plesiosaur relative, preserved from 78 million years ago, was found with an embryo still inside its body. The skeleton told a story that had been invisible before. Plesiosaurs gave birth to live young. They did not lay eggs. They carried developing offspring internally, bringing them to term in open water, delivering calves directly into an ocean that had never known any other home for the creatures they carried. But the reproduction strategy revealed was even more extraordinary than viviparity alone. The fossil showed not a clutch of small offspring, the way most reptiles reproduce, but a single large calf. The fetus occupied approximately 35% of the mother's body length at near term, a massive investment in one offspring. This strategy mirrored what whales do, what elephants do, what great apes do. It was K-selection, the reproductive philosophy of animals that live long lives, reproduce infrequently, and invest everything in ensuring that each offspring survives to adulthood. Most reptiles scatter their young and abandon them. Plesiosaurs did the opposite, binding themselves to a single calf through months of internal development. Abyssosaurus almost certainly followed this identical pattern. It produced a single large calf, born in open water, possibly in the dim upper reaches of the sea, where it could still breathe air before beginning its descent into the realms its mother inhabited. The inheritance that calf received at birth was already written into its skeleton: dense bones that would allow it to sink, large eyes that would eventually learn to hunt in darkness, a short triangular skull and narrow jaw ready for the work of ambush. The young animal was born ready for a life that existed nowhere else on Earth, in a realm that had no surface, no escape to warmth or light. The specimen of Abyssosaurus, the single skeleton that has survived 130 million years, may hold one more secret. Beside the adult remains, another shape appears in the rock, a smaller skeleton that has never been formally described or confirmed. Whether this represents a calf that died alongside its mother, or simply the chance positioning of bones from different individuals, remains uncertain. The scientific record has not yet finished reading what those two shapes might mean, what story they might tell about reproduction in the abyss, about mothers and young in a realm where survival demanded everything and mercy was unknown. The cryptoclidid family was fading by the time the early Cretaceous arrived. Elasmosaurids, a different plesiosaur lineage with extreme necks and specialized hunting strategies, were diversifying across the world's oceans, colonizing niches that cryptoclinids had occupied for millions of years. The competition was not violent or sudden, it was the slow reshaping of available space, the gradual contraction of territory as new strategies proved effective and older ones lost their advantage. Most cryptoclinids responded by staying where they had always been, in moderate depths and surface waters, hunting the same prey in the same ways their ancestors had perfected. They did not adapt. They simply persisted in their traditional niches until those niches became too crowded. Abyssosaurus chose differently. It abandoned the competition entirely, sinking into the one realm no other cryptoclidid had learned to exploit. This decision, if it can be called a decision across millions of years of gradual evolution, may have been precisely what allowed the family to survive in Russian waters long after most other cryptoclinids had vanished elsewhere. By occupying the deep, Abyssosaurus found a niche with no competitors, a space where the expanding elasmosaurids had never learned to hunt, where no other plesiosaur had developed the specialized adaptations required to thrive. Abyssosaurus represents the first and only confirmed record of Cryptoclididae in Russian waters. This is not simply a new species from a known family. It is a new geographic fact, evidence that the family had ranged further east across the Tethys than anyone had previously discovered. The fossils that had been collected from other regions had mapped the family's known distribution, and Russia was not part of that map. Abyssosaurus expanded the boundary, suggesting that the cryptoclinids had been more widespread, more ambitious in their exploration of available seas than the fossil record had previously indicated. Its position in the family tree proved complicated. When first described in 2011, Abyssosaurus was assigned to Aristonyctidae, a different family of elasmosaurids based on features of its skeleton that seemed to align with that group. 2 years later, in 2013, a broader phylogenetic analysis by Roger Benson and Patrick Druckenmiller relocated it to Cryptoclididae, positioning it near Collembosaurus and other members of the family. The bones had resisted easy categorization, which reflected something profound about the animal itself. It did not fit neatly into existing categories because it was not easily categorizable. It had evolved in isolation, adapting to an environment so different from its relatives that the usual diagnostic features had shifted, had changed proportions, had become ambiguous. This ambiguity in classification mirrors the ambiguity of the animal's place in evolutionary history. Abyssosaurus sits phylogenetically between late Jurassic forms like Tatanectes and Chimerosaurus, and late Cretaceous ones like Aristonectes and Kiewikia. It is a bridge between two eras of plesiosaur evolution, yet it was found in a place where no bridge was expected to exist. The deep sea had preserved a creature that occupied an unexpected moment in time, an unexpected geography, an unexpected way of being a plesiosaur, when the plesiosaur lineage was supposed to be moving in other directions entirely. Around 130 million years ago, the oceans shifted, not suddenly, not catastrophically, but through the slow rearrangement of currents and circulation patterns that had maintained the Tethys for millions of years. The Pharaonic anoxic event began, a period when oxygen levels in deep and mid-water zones declined across multiple ocean basins. This was not suffocation of the entire ocean. Rather, it was a collapse of oxygen availability in the layers where Abyssosaurus hunted, a gradual drowning of the very environment the animal had specialized for. Oceanic anoxic events are episodes when the machinery of ocean circulation falters. Surface waters warm and become less dense, reducing their ability to sink and carry oxygen downward. The deep waters, cut off from replenishment, exhaust their dissolved oxygen through the respiration of organisms that depend on it. In the most severe zones, oxygen disappears entirely, leaving only anaerobic conditions where decomposition cannot occur. The organic matter that dies accumulates and preserves itself in dark sediments rich with the chemistry of decay. These become black shales, a geological signature of a world without breath. The bathyal zone, the realm Abyssosaurus had committed itself to, was among the most vulnerable. The deep is fragile in ways that surface waters are not. Oxygen enters from above, transported by sinking water masses. If circulation falters, if that transport mechanism breaks, the deep becomes a tomb. The ecosystems that had evolved to thrive in that environment depend on steady oxygen supplies. When those supplies dwindle, the web of life that sustains the prey Abyssosaurus hunted begins to collapse. The sea that covered what would become Chuvashia was already precarious. It was a semi-enclosed arm of the Tethys, not an open ocean basin. Semi-enclosed seas are particularly vulnerable to anoxia. They have limited exchange with the broader ocean, limited replenishment of oxygen, limited escape routes for life when conditions deteriorate. As the Pharaonic event intensified, this inland sea felt the effects more acutely than distant ocean basins might have. The oxygen that had made the depths habitable began to vanish. Abyssosaurus found itself caught between collapsing pressures. Above, the competitive world remained hostile. Elasmosaurids and other predators still occupied the surface and mid-depths, territories the plesiosaur could not reclaim. Below, the environment that had seemed like refuge was becoming uninhabitable. The prey species that Abyssosaurus had learned to hunt in darkness were struggling to survive in water that was losing the oxygen they needed. The cephalopods and crustaceans, the soft-bodied creatures that formed the diet of the deep specialist, were retreating to whatever pockets of better oxygenated water remained, or dying as conditions worsened. The cryptoclidid line was already thin by this point. Abyssosaurus was not simply one animal facing ecological pressure from above. It was the last representative of a family lineage, contending with environmental pressure from below as well. A specialized predator in a narrowing niche, adapted perfectly for conditions that were ceasing to exist. The dense bones that had served it so well, the large eyes calibrated for hunting in darkness, the patient metabolism that had allowed decades of slow hunting. None of these adaptations could answer the fundamental problem. The deep was changing, and Abyssosaurus had no alternative strategy, no way to return to the shallows, no second life available if the abyss became hostile. Specialists are the most elegant and the most vulnerable of evolution's creations. A generalist survives through adequacy, through the ability to do many things reasonably well. A specialist survives through excellence at one thing, through perfection of a single strategy, through the refinement of a niche into an art form. But this excellence carries a price. The moment the niche changes, the moment the world shifts in a direction the specialist cannot follow, survival becomes impossible. There is no fallback position, no second strategy evolved over millions of years, no alternative way of being. Abyssosaurus was the deepest specialist its family had ever produced. The cryptoclidids before it had specialized in fish and cephalopod hunting, but they had done so in moderate depths, in zones where conditions remained relatively stable across millions of years. Abyssosaurus had pushed specialization to an extreme. It had committed entirely to the bathyal zone, to darkness and pressure and cold, to a way of life that demanded dense bones and enlarged eyes and a metabolism calibrated for patience. Every aspect of its body was an investment in that single niche, a bet placed on the permanence of the deep. When the niche degraded, Abyssosaurus had no escape. The anoxia that spread through the depths made hunting impossible as prey disappeared or suffocated. The cooling that accompanied the environmental shift altered the chemistry of the water in ways the animal's physiology could not accommodate. The semi-enclosed sea that covered Chuvashia was slowly losing its connection to the broader Tethys, becoming more isolated, more vulnerable to local environmental collapse. The conditions that had allowed the deep to function as a refuge were evaporating. The cryptoclydid family faded from the fossil record during the early Cretaceous. Not all at once, not in a dramatic extinction event, but gradually, region by region, replaced by other plesiosaur lineages, better suited to the seas that were emerging. Leptocleidids, a different family, rose to prominence in some regions. Elasmosaurids, with their extreme necks and specialized feeding strategies, diversified explosively, coming to define what long-necked plesiosaurs would mean for the rest of the Cretaceous period. The cryptoclydids did not vanish in a moment. They simply ceased to compete effectively in a world that was reorganizing itself around different solutions. Abyssosaurus appears in the record as one of the last of its kind in Russian waters. Not a survivor in any heroic sense, but a terminus, the final representative of a family lineage that had persisted for 40 million years, ending in a sea that was itself ending. The animal that had engineered itself so perfectly for the abyss found that perfection offered no protection against change. Most extinctions do not resemble the catastrophic moments imagined in popular understanding. Abyssosaurus did not perish in an instant of planetary upheaval. It died the way most extinctions actually occur, slowly, as the world changed faster than a body could adapt, as the conditions that had allowed one particular way of living gradually became incompatible with survival. The deep that had been home became a trap. The specialization that had been advantage became liability. In the end, Abyssosaurus simply ran out of options in an ocean that no longer had room for what it was. The sea that held Abyssosaurus no longer exists. The epicontinental seaway that covered what is now the Chuvash Republic 130 million years ago has vanished completely, leaving no trace on the surface of the world. The Cretaceous period continued for another 65 million years after Abyssosaurus died, and during all that time, the geography of the planet rearranged itself. Sea levels fell as the climate cooled. Continents drifted, their positions shifting fractions of inches across geological time. The arms of the Tethys Sea that had penetrated deep into Europe and Russia, that had filled the spaces between continents with warm tropical water, slowly retreated into smaller and smaller domains. The Tethys itself persisted for a very long time, but eventually it too closed. Approximately 50 million years ago, the African plate collided with the Eurasian plate, a continental merger that squeezed the seaway from the south and eliminated the remaining passageways through which ocean water had flowed. The great tropical seaway that had divided the world for hundreds of millions of years compressed into fragments, into remnants that would become the modern Mediterranean Sea, the Black Sea, and the Caspian Sea. These inland waters are all that survives of that vast system, the only reminder of an ocean that once stretched across latitudes and shaped the climate and biology of an entire hemisphere. Where Abyssosaurus hunted in darkness, rolling steppe now exists. The Sura River winds through agricultural land and forest, its banks composed of sediment that was laid down on an ocean floor more than 100 million years ago. The limestone and shale that form these banks are the compressed remains of an ancient seafloor built from the bodies of ammonites and belemnites and fish, from the skeletons of creatures that sank through the water column and accumulated in layers over millions of years. This rock remembers what the land has forgotten. It carries the history of a world that vanished. The bones of Abyssosaurus are locked within that sediment, preserved in marine limestone, stone formed from the calcium carbonate shells, and skeletal structures of creatures that lived in the vanished sea. The animal that descended to the bathyal zone, that hunted in darkness and pressure, is now part of solid rock. The water column that once stretched thousands of feet above the seafloor where Abyssosaurus died has compressed into stone, has transformed into something entirely different. What was once the abyss is now merely another layer of strata, buried and compressed, miles above sea level relative to where the ancient seafloor actually was. The transformation is almost incomprehensible. The realm Abyssosaurus perfected itself for, the deep zone of darkness and cold and pressure, no longer exists in any recognizable form. The bathyal zone of that vanished Tethys arm has been lifted by tectonic forces, exposed to weathering and time, become part of the continental landscape. The abyss that shaped every dense bone and enlarged eye eventually became ground. Abyssosaurus chose the deep as its home, and the deep became permanent in a way the animal could never have anticipated, transformed not into the surface world it occasionally visited for air, but into solid earth, into rock, into something that no longer breathes or holds water or remembers what it once was. 1992. A man named Vasily V. Mita walked along the banks of a tributary of the Sura River in Poretsky district, Chuvashia, working the exposed sediment where geology meets the surface. He found bones, partial, scattered through marine limestone, arranged in a way that suggested they had once belonged to a single animal. The bones were recognizably plesiosaur. Their shape and structure proclaimed their identity even in fragmentation. They were partly articulated, meaning some had retained their anatomical relationship to one another, suggesting rapid burial rather than long dispersal. The sediment that held them was dated to the Hauterivian stage, approximately 133 to 130 million years ago. The specimen was collected carefully and transported to the Museum of Chuvash Natural Historical Society, a provincial institution in a region where paleontological discovery was uncommon. It was catalogued as specimen MCHEIOPM1, given a designation that would be its only name for many years. Few people knew of its existence. It sat in storage, bones waiting for the attention that would eventually come, though no one could have predicted the significance those bones would eventually reveal. In 2011, a scientist named Alexander U. Berezin published the first formal description. He named the creature Abyssosaurus natalii, establishing it as a new genus and a new species. The species name honored Natalia Berezina, his wife and research associate. The description was based on postcranial evidence, the bones of the body and skeleton that did not include the skull. Berezin assigned Abyssosaurus to Aristonectidae, a family of elasmosaurids, relying on features that seemed to align the creature with that group. The skull remained unrecognized at that time, still mixed with other bones in the museum collection, its significance unnoticed. 2 years later, in 2013, a broader phylogenetic analysis conducted by Roger Benson and Patrick Druckenmiller examined Abyssosaurus alongside a wider range of plesiosaur species. The analysis incorporated more complete data and employed more sophisticated methods of comparison. The results relocated Abyssosaurus entirely, moving it from Aristonectidae to Cryptoclitidae, positioning it near Columbosaurus and other genuine members of that family. The original classification had been wrong. This was not a failure. This was science functioning exactly as it should function. The initial description had been based on incomplete data, on the best understanding possible with the information available at that time. New analysis, incorporating new perspectives and more comprehensive comparison, had revealed that understanding to be incorrect. The revised classification was closer to truth. This is the mechanism by which scientific knowledge improves. Hypotheses tested against new evidence, conclusions revised when evidence demands it, truth approached gradually through successive refinements. Each step forward builds on the previous one, acknowledging what was learned while moving toward accuracy. Abyssosaurus had been sitting in a provincial museum the entire time, waiting to be fully understood. The bones that Vasily Mita had collected from a riverbank carried secrets that would take years to uncover, classification that would shift and settle and shift again as knowledge accumulated. The specimen that seemed to be merely another fossil in a regional collection would eventually reveal itself as something far more remarkable. A creature that had solved the problem of the deep in a way that evolution would not solve again until mammals had evolved and the continents had moved to their modern positions. When Alexander Berezin first prepared the specimen in 2011, the skull remained invisible, not because it was absent from the collection, but because it had not been recognized for what it was. The cranial elements, the bones that form the head and face, had been packed into the area of the pectoral girdle, the shoulder region where they had come to rest after death and burial. They were pressed against the body bones so intimately that in the initial field preparation, they had become indistinguishable from the surrounding material. A skull is not always obvious. When fragmented and displaced, when mixed with the skeleton of an animal that died in soft sediment, it can disappear entirely into the general collection of bone. For 7 years, the skull of Abyssosaurus sat in the museum. It occupied space and storage, mixed with other bones from the same specimen, handled and cataloged and stored away. People looked at the collection. Scientists examined the remains. No one recognized what they possessed. The skull waited in the dark, its secrets intact, its significance unnoticed. 7 years is a long time for a fossil to exist without being seen, even when it has been found. In 2018, Berezin returned to specimen MCHEIOP-M1. He looked again at the bones that had seemed unremarkable in 2011. This time, he recognized the cranial material. He saw what had been there all along. The skull emerged from the bones that surrounded it, as if perception itself had brought it into being. He published a second paper describing the cranial elements in detail, a description of the same specimen that had been partially described 7 years before. The paper focused on what the skull revealed, the anatomy that proved the animal's deep-water specialization, the structure that confirmed every inference the body had already suggested. A third paper followed in 2019. This one addressed the morpho-functional features, the way the skull's structure related to function, to how the animal actually lived. This paper incorporated the sperm whale comparison, the analysis of the retia mirabilia, the reasoning that connected bone structure to behavior and ecology. It told the story of what Abyssosaurus actually was, not simply what its skeleton looked like, but what the skeleton meant about its life and its world. Three papers across 8 years, all describing the same single skeleton. 30 years, from the moment Vasily Mita found the bones on a riverbank to the point when the full story was finally understood. The skull that explained everything had been present from the beginning, had been collected with the rest of the skeleton, had been sitting in a museum, waiting to be recognized. It required nothing but the patience to look again, to approach the same specimen with fresh eyes, to understand that what seemed like undifferentiated bone might contain secrets worth discovering. The incompleteness of knowledge persists, even when all the evidence is present. A fossil does not yield its meaning all at once. Understanding accumulates through repeated examination, through the willingness to reconsider what has already been found, through the recognition that the most important discoveries sometimes involve not finding something new, but recognizing what has been there all along. There is only one Abyssosaurus, not one species represented by multiple specimens, not one site yielding dozens of individuals, but a single animal, one death, one set of bones preserved in sediment. Everything known about this creature originates from that singular skeleton and the skull that remained hidden within it for years. The depth it inhabited, the strategy it employed, the way its biology converged with creatures separated from it by 107 million years, its position in the plesiosaur family tree, its role in an ecosystem that no longer exists. All of this has been reconstructed from partial remains of one individual. Consider the improbability of what that means. An entire life, potentially decades spent in darkness and pressure, reduced to fossilized bone. The animal died in one moment, at one location, in sediment that happened to preserve its skeleton in a way that would survive 130 million years of geological transformation. The bones had to avoid being broken and dispersed. They had to resist dissolution in groundwater. They had to persist through the compression and heating that accompanies burial. They had to be exposed, after all that time, in a place where a paleontologist named Vasily Mita happened to be walking along a riverbank. Every step in this chain of improbability had to align perfectly for us to know Abyssosaurus exists at all. The information density of a single fossil is staggering. Each bone carries meaning. The pachyostotic ribs that were thickened and dense did not become that way by accident. They represent an evolutionary decision made across millions of generations, a commitment to sinking rather than floating. The enlarged orbits that retain juvenile proportions into adulthood embody the decision to hunt in darkness, to invest in vision when light does not penetrate. The short triangular jaw, narrow and precise, records the decision to ambush rather than chase, to grasp rather than tear. The wide chest and reinforced skeleton encode decisions about how to move through water, how to regulate pressure, how to distribute mass. All of those decisions were made by evolution, not by conscious choice, but through the relentless culling of variation across millions of generations, through the survival of individuals whose bodies happened to be suited to the environment they occupied. Those decisions are all present in one set of bones. The entire history of how Abyssosaurus came to be the way it was lives in specimen MCHEIOPM1, stored in a museum in Cheboksary, Russia. This singular skeleton is the entire fossil record of a creature that lived for decades. No growth series showing how the young developed. No population statistics revealing how common or rare the species was. No geographic distribution showing whether other populations existed elsewhere, just one animal, at one moment, preserved well enough for science to eventually recognize what it represented. That one skeleton contains more information about deep water predation in the Cretaceous than any other source available. The evolutionary experiment that produced Abyssosaurus left behind only this: one body, one story, one chance to understand a life lived in the abyss. Everything we know of Abyssosaurus exists because that single animal died in exactly the right place at exactly the right time and was eventually found. Convergent evolution stands among biology's most philosophically profound phenomena. It occurs when unrelated lineages, separated by vast stretches of time or geography, independently develop similar traits. Ichthyosaurs and dolphins offer a classic example, both streamlined, both bearing dorsal fins, both adapted for fast hunting in open water. One was a reptile, the other a mammal, separated by 250 million years of Earth's history. Yet they solved the problem of aquatic predation by arriving at nearly identical body plans. Pterosaurs, birds, and bats all invented flight, each lineage developing wings through completely independent evolutionary pathways, yet all achieving aerial locomotion through functionally similar structures. The convergence between Abyssosaurus and sperm whales transcends these examples in a crucial way. It is not merely a body shape that repeated, it is an entire strategy, a complete philosophy of how to exist and hunt in an extreme environment. Both animals are air breathers, creatures that require regular contact with the atmosphere to survive. Both weighted their bodies deliberately, increasing density to counteract buoyancy. Both descended to depths where pressure reaches hundreds of times atmospheric force. Both hunted in absolute darkness, using the limited sensory information available in that realm. Both underwent the exhausting cycle of descent and ascent, diving deep to feed and then climbing through vast water columns to breathe. This is not convergence of isolated features. It is the convergence of an entire integrated strategy, a way of being that required changes to multiple body systems working in concert. The dense skeleton of Abyssosaurus and the density of whale fat and muscle serve the same function. The enlarged eyes of Abyssosaurus and the sophisticated sonar of whales both extract meaning from an environment that provides very little perceptual information. The patient metabolism of one and the precise oxygen management of the other both reflect an adaptation to scarcity and patience rather than speed and abundance. The deep sea appears to function as a problem with a particular shape. Whatever enters that realm from the surface world faces the same constraints: extreme pressure, complete darkness, scarcity of food, cold that saps energy efficiency. An air breather attempting to hunt in that environment must solve an identical puzzle: how to descend without being crushed, how to see without light, how to hunt prey that cannot be chased, how to return for air without wasting the energy gained from a successful hunt. Evolution arrived at essentially one answer to this puzzle, and evolution found that answer twice, across more than 107 million years, in completely unrelated lineages. This convergence suggests something profound about the nature of environmental constraint. The deep sea does not merely provide habitat, it exerts directed pressure on the bodies and behaviors of air breathers that enter it. It bends evolution toward particular solutions because very few solutions actually work. A light skeleton fails, density succeeds. Small eyes fail, large eyes succeed. Speed fails, patience succeeds. The environment does not determine evolution precisely, but it narrows the range of viable possibilities so dramatically that the same answer emerges repeatedly. The deep sea is not simply a place, it is a kind of problem, and both Abyssosaurus and sperm whales represent evolution's answer to that problem, discovered independently across the immensity of geological time. The Russian Hodorivian seas held an abundance that extended far beyond the depths where Abyssosaurus hunted. Every layer of the water column hosted specialized predators and prey, each occupying territories shaped by millions of years of adaptation. Luscon italensis patrolled the mid-depths, a plesiosaur discovered and described in 2017 from the Ulyanovsk region, living in the same era and the same sea as Abyssosaurus. It carried a skull remarkably slender and refined, more similar to the polycotylids than to typical pliosaurs, and measured 16 to 20 feet in length. Where Abyssosaurus had descended into darkness, Luskin hunted in the twilight zones and upper reaches, pursuing prey in water where some light still penetrated, where speed and power conveyed advantage. Ophthalmosaurid ichthyosaurs moved through these same waters with the efficiency of modern dolphins. Streamlined bodies, large forward-facing eyes, and powerful tails made them apex predators of the mid-column, capable of pursuing fast-moving fish and smaller cephalopods. They operated on timeframes measured in seconds and minutes, diving and climbing and hunting with the precision of pursuit predators. The contrast between their strategy and Abyssosaurus's patience could not have been sharper. One lineage had invested in speed, the other in stillness. Ammonites existed in extraordinary diversity throughout the water column. Cymberschites and Spitanoceras and dozens of other coiled cephalopod species occupied their own ecological tiers, each adapted to particular depths and temperature zones. When they died, their shells sank slowly downward, a constant rain of organic material descending through the water column. Some of this material reached the depths where Abyssosaurus hunted, providing a steady, if sparse, supply of nutrition that had originated in shallower, more productive waters above. The coiled shells accumulated on the seafloor, and many became fossils themselves, their abundance in the rock record testifying to their former prevalence. Early sharks moved through their own ecological lanes, diversifying and experimenting with body plans that would eventually lead to the modern forms that dominate oceans today. They occupied multiple niches across the water column, competing with ichthyosaurs and plesiosaurs for access to the same prey species, yet each lineage finding space through specialization and behavioral separation. This was a complete ecosystem in the fullest sense. The surface and upper waters hosted their own communities, the mid-depths their own predators and prey, and the deep its own sparse but persistent life. Abyssosaurus had claimed the one tier where no other plesiosaur had developed the adaptations to thrive. The cost of living there was steep: heavy bones, slow metabolism, tolerance for pressure and cold. Most predators could not afford to pay that price. They remained in warmer, more abundant waters, where energy was easier to obtain and reproduction more feasible. The refuge that the deep provided was not safety in any conventional sense. Plesiosaurs were large animals, and size invited predation even in the depths. Rather, the refuge lay in competition. It was the absence of rivals, the claiming of a niche that no other creature had learned to exploit. In an ocean crowded with predators competing for the same fish and squid and crustaceans, Abyssosaurus had found the one empty layer, the one realm where its particular constellation of adaptations gave it an uncontested advantage. The deep was lonely, but it was uncontested. The neck of Abyssosaurus extended from a body that was relatively compact, a moderate length compared to the extreme elongations that would characterize elasmosaurids in later periods, yet notably longer than what pliosaurs possessed. Research on related cryptoclitids, such as Cryptoclidus euramaris, has revealed something unexpected about these structures. The neck, despite its length, operated under significant constraints. Vertebrae articulated in ways that severely limited lateral movement. The neck could not sweep side to side with the fluidity that conventional predatory anatomy would suggest. It could not function as a whip or as a flexible striking instrument. Instead, scientists proposed an alternative function. The neck may have served as a form of camouflage, both visual and hydrodynamic. Picture the feeding strategy: a large body full of organs and muscle and heavy bone positioned at distance. From that body extends a long, slender neck, at the end of which sits a small, triangular skull with a narrow jaw. The prey sees not the bulk of the predator, but only the narrow stalk approaching, a shape far less threatening than a full-sized plesiosaur head advancing through open water. Schooling fish or small cephalopods might not recognize danger until the small head was already close enough to strike. The body remained hidden, withdrawn, unthreatening, while the reaching neck allowed the head access to prey that might otherwise have fled. In Abyssosaurus, this strategy underwent transformation. The depths held no visual light, no bioluminescent schools of fish at sufficient density to make camouflage a useful strategy. The neck could not hide what it was meant to hide in total darkness. Instead, the reach mechanism persisted, but its function shifted fundamentally. The long neck allowed the small skull to explore the sediment, to probe into crevices and under rocks, to approach patches of seafloor where prey sheltered, all while the body remained suspended above, undisturbed, maintaining position. The neck became not a visual deception but a practical tool, a reach that extended the skull's access to territory without requiring the entire animal to venture into spaces that might be cramped or dangerous. The body itself could hover motionless, suspended by the angled flippers and dense skeleton. The neck could bend and stretch, could move the skull through confined spaces, could position the small jaw exactly where prey had concealed itself. A neck as a reaching arm, a skull functioning like a hand. The long vertical stalk was not built for speed or for sweeping strikes. It was built for precision, for access, for the careful exploration of a three-dimensional space where most predators dared not venture. This transformation of function illustrates how evolution repurposes structures. The neck inherited from earlier cryptoclitids carried the anatomical constraints of its ancestors, the limited lateral mobility that had once served to hide a large body while a small head approached. In darkness, that constraint became irrelevant. The reach persisted, freed from the need to deceive, simply serving as an extension of the hunting mechanism. Abyssosaurus had taken an ancient adaptation and twisted it to new purposes, finding utility in properties that had evolved for entirely different reasons. The deep sea selects ruthlessly for patience. In shallows and surface waters, prey is abundant enough to reward speed, aggression, burst energy expenditure. A predator that can chase faster, strike harder, recover quicker, gains access to food that constant activity makes available. The deep operates under entirely different constraints. Prey scatters thinly through the water column. Encounters arrive rarely, separated by hours or days of cruising through darkness. Energy spent in fruitless pursuit is energy wasted, energy that cannot be recovered from meals that may not arrive. The only viable strategy is conservation. Every movement must count. Every calorie must be justified. Abyssosaurus embodied this philosophy completely. Its dense bones, heavy and expensive to build, required substantial energy investment during growth. But once constructed, those bones demanded less ongoing metabolic cost to maintain than lighter skeletons would have. The density served its function continuously. The initial expense was paid once, then the advantage accrued indefinitely. The propulsion generated by its hind flippers emphasized cruising rather than acceleration. Long, slow movements through water use less energy than frequent bursts of speed. The jaw, short and precise, struck and held prey rather than biting and shaking with the violence that speed hunters employ. Every anatomical feature reflected an organism that had been shaped by scarcity, by the understanding that the next meal could not be guaranteed. Modern deep sea specialists reveal how consistent these pressures are across unrelated lineages. Sperm whales maintain slow heart rates during dives, reducing oxygen consumption. Elephant seals exhibit extreme oxygen efficiency, storing oxygen in muscles and blood rather than wasting it on metabolic inefficiency. Giant squid hunt patiently in waters where food arrives unpredictably. All of these creatures, descended from surface-dwelling ancestors, have been reshaped by the deep into recognizably similar forms: conservative metabolisms, slow movements, extended patience between feeding events. Abyssosaurus was a reptile, not a mammal, and its metabolic regulation differed fundamentally from modern marine mammals. Reptiles cannot control body temperature the way mammals do. They cannot maintain the elevated metabolic rates that mammals require. Yet, the pressures that shaped modern marine mammals shaped Abyssosaurus identically across 130 million years of separate evolutionary history. The outcomes converged: conservative physiology, slow cruising, patient hunting, low resting, metabolic rates calibrated to scarcity. This animal lived in slow motion relative to its surface-dwelling relatives. The currents above the depths carried ichthyosaurs and pliosaurs, moving with purpose, pursuing prey, engaging in the constant activity that shallow life demanded. Abyssosaurus descended into a realm where such hurry was not merely inefficient, but actively dangerous. Wasting energy in the deep meant starvation. There was no abundance to recover from profligacy. The animal that evolved there had to internalize patience at every level, from bone structure to muscle fiber to the rhythm of its hunting behavior. Every system operated at reduced pace. Heart rate stayed low. Movement stayed deliberate. The cycles of feeding and fasting stretched across time frames measured in days rather than hours. An organism entirely calibrated to scarcity and pressure and dark, shaped by an environment that rewarded nothing so much as the wisdom to move through it conservatively, taking only what was necessary, wasting nothing, and always waiting for the next rare opportunity to feed. Chuvashia occupies inland territory in modern Russia, landlocked and forested, separated from any ocean coast by approximately 375 miles. The landscape is rural, dominated by rolling steppe and river valleys. Agricultural fields stretch across land that was once seafloor. The Sura River winds through this terrain, its current modest and unspectacular, its banks composed of sediment that carries no obvious announcement of what lies beneath. A visitor walking along those banks would see nothing to suggest that 130 million years ago, water covered everything. Yet the rock exposed in Poretsky district is Hauderivian limestone, marine sediment laid down in an ancient sea. This stone formed from the accumulated bodies of creatures that lived in depths and currents that no longer exist. The limestone itself is the compressed remains of that vanished ecosystem. Abyssosaurus rests within it, preserved in a form so complete that scientists can extract decades of information from a single skeleton. The Chuvash National Museum in Cheboksary holds specimen MCHEIOPM1. Cheboksary is a regional center, a few hours' drive from Moscow, but it receives a fraction of the scholarly attention granted to major paleontological institutions in London or New York or Beijing. The museum is underfunded and understaffed, like most regional institutions that hold paleontological collections. Researchers must travel to access the specimen. Students rarely visit. International scholars are uncommon. The only known Abyssosaurus exists in a place that most people have never heard of, in a repository that operates far from the centers where major paleontological research occurs. This geography of obscurity is not exceptional in paleontology. Most of the fossil record of life on Earth rests in regional museums, in university collections, in storerooms that few people ever enter. The major specimens that attract media attention and popular knowledge represent a vanishingly small fraction of what has been discovered and preserved. A museum in a remote region of Russia might hold specimens as significant as anything in more famous institutions, yet they remain largely unknown to the world because geography and language and funding have isolated them from broader scientific conversation. Alexander Berezin worked with this specimen for 3 decades, publishing descriptions slowly across a span of years, refining understanding as new data emerged. He labored in relative obscurity, publishing in journals that most paleontologists outside his field might never read. His contributions to understanding deep-water predation in the Mesozoic have been substantial, yet they remain known primarily to specialists. The creature he described, the animal that solved the problem of abyssal life in a way that would not be solved again until mammals evolved, exists in a regional museum in a landlocked republic, held in obscurity by the very geography that once allowed the Tethys Sea to cover this land. This is the paradox of paleontological significance. The creature that figured out how to live and hunt in the deep 107 million years before sperm whales arrived at the same solution then remains in a place most of the world will never visit. The fossil that carries extraordinary information about convergent evolution, about specialization, about the deep sea, as an environment that shapes evolution toward particular solutions, sits in storage in Cheboksary, waiting for the next researcher patient enough to look, to ask new questions, to extract further meaning from the bones that Vasily Mita found along a riverbank 30 years ago. The bathyal zone carries sound that human ears would not recognize as sound. Pressure waves propagate through water at different speeds than through air, carrying information across distances in ways that surface dwellers never experience. The water column creaks under its own weight, compressing and shifting as currents move through it. Bioluminescent organisms flash in the darkness, producing patterns of light that communicate meaning to other creatures in that realm, though the messages remain opaque to any observer from the surface world. The deep is not the absence of sensation. It is the presence of sensations so alien that they resist translation into human language. What Abyssosaurus perceived in that environment remains locked away. We can examine the anatomy of its skull, measure the size of its eye sockets, map the structure of its inner ear, and still fail to reconstruct the subjective experience of navigating that realm. The animal possessed large eyes, calibrated to gather photons in dim light, yet no photons penetrated to the deepest depths. Bioluminescence from other creatures provided the only illumination, fleeting flashes that appeared and disappeared, offering fragmentary information about what moved in the darkness. The plesiosaur inner ear was not constructed for echolocation. The sophisticated biological sonar that modern toothed whales employ. Abyssosaurus likely navigated by integrating multiple sources of information, the capture of whatever bioluminescent signals reached it, sensitivity to pressure waves through a lateral line system that most reptiles possess, perhaps even electromagnetic sensitivity that modern sharks demonstrate. A sensory world assembled from inputs that had no human parallel, no familiar framework for understanding. The animal rose periodically from that realm of alien perception to a place equally foreign in its own way. The surface was warm, where light penetrated down from above, where the water held dissolved oxygen at higher concentrations, where the pressure that shaped the depths released its hold. Abyssosaurus returned to air, breaking the surface of a Hauterivian sea that was already beginning to change, already becoming hostile to the specialized life that inhabited its depths. The animal that had engineered itself for the abyss spent these surfacing moments in a world it barely belonged to anymore. Its dense skeleton, so perfectly adapted for depth, worked against it in shallow water. Its large eyes, evolved to capture faint bioluminescence, were overwhelmed by the glare of sunlight. Its patient metabolism, calibrated to the scarcity of the deep, encountered an abundance above that meant nothing to an organism built for hunger and constraint. The surface was necessity, a biological obligation that could not be escaped. Every breath required a journey from depth to light, from pressure to atmospheric air, a journey the animal made repeatedly across decades of its life. The abyss was home in the only meaningful sense. It was the environment that the animal's entire body had been shaped to inhabit. The patterns of its existence formed a cycle: descent into darkness, hunt in pressure and cold, ascent to an alien surface, breath taken in a world that had no place for such creatures, then descent again, back to the realm where every bone and every sense functioned as intended, where the animal was finally, completely itself. Science defines itself as much through what it cannot discover as through what it reveals. The single skeleton of Abyssosaurus carries extraordinary information, yet that information is surrounded by absences, by questions that the fossil record cannot answer. Every gap in understanding points towards something that has been lost to time, something that will remain unknown unless fortune provides another specimen. The size of Abyssosaurus at death cannot be determined with certainty. The skeleton may represent a young animal still growing, a mature individual in its prime, or an elderly creature at the end of a long life. Without comparative specimens showing the full range of growth from juvenile to old age, paleontologists can only estimate. The proportions suggest a certain size range, but precision is impossible. How much larger might Abyssosaurus have grown? How small might it have been at birth? These questions lack answers. Coloration exists entirely beyond recovery. Modern deep-sea animals display an extraordinary range. Some are transparent, others pitch black, still others covered in bioluminescent photophores that generate their own light. What color was Abyssosaurus? Black, to absorb any light in the depths? Transparent, to disappear into darkness? Patterned in ways that communicated with others of its kind? Bone preserves structure, but not pigment. The skin and scales that once covered this skeleton have vanished, leaving no trace of how the animal appeared in its own time. Longevity remains speculative. The dense bones and slow metabolism suggest decades of life, possibly longer than most surface-dwelling relatives lived. But confirmation requires sectioning bone to count growth rings, a process that has not yet been performed on this specimen. Whether Abyssosaurus lived for 20 years or 80 years or some number in between cannot be known from external examination alone. Sociality is unknowable. The K-selected reproductive strategy of plesiosaurs broadly suggests the possibility of family groups, of herds that move together through the ocean, of parental investment in young animals. But one skeleton provides no evidence either way. Was Abyssosaurus solitary, encountering others of its kind only to reproduce? Did it live in groups, hunting together, providing mutual defense? The fossil offers no answer. Communication methods lie beyond inference. Did Abyssosaurus produce sounds to navigate or signal? Did it navigate by landmarks, returning repeatedly to the same feeding grounds? Did it possess migratory behaviors, traveling vast distances across ocean basins? Did it rest at depth or climb to the surface to sleep in warmer water? Every aspect of behavior beyond eating and reproduction remains locked in mystery. These absences are not failures of science. They are the honest boundaries of what fossils can reveal. Bone preserves structure and function. It cannot preserve color, behavior, or the texture of social relationships. Every unknown is a question that could only be answered by finding more specimens, by accumulating comparative material that allows paleontologists to see patterns, to establish ranges, to distinguish individuals from populations. So far, the fossil record has provided only one Abyssosaurus, one animal, one death, one set of bones that speaks clearly about anatomy and ecology, but remains forever silent on everything else. The specimen description contains a detail that has never been fully explored. Alongside the adult skeleton, researchers noted the possible presence of a second, smaller set of bones. The description offers no elaboration, no formal analysis, no confirmation. It appears in the literature as a suggestion, a possibility mentioned in passing, a detail that awaits examination. The second shape lies in the same rock that held the first, positioned close enough to suggest connection, yet separated by years of scientific neglect. This smaller skeleton has not been formally described. It exists in a liminal space, between discovery and interpretation, between possibility and certainty. If the bones belong to a fetus, if they represent a young animal developing inside the adult, then Abyssosaurus would become only the second plesiosaur ever discovered with direct evidence of reproduction. The first was that Polycotylus from Kansas, found 78 million years ago with an embryo preserved inside its body. But Polycotylus hunted in warm, moderate depths. Abyssosaurus would be entirely unique, the only deep-sea specialist among all known plesiosaurs to show evidence of carrying young. What does this juxtaposition mean? Two animals, one fully formed and one not yet complete, came to rest together in sediment 130 million years ago. They remained together through geological transformation, through compression and heating and the countless processes that convert soft tissue and bone into stone. They survived the passage of 130 million years in the same rock, in the same location, in the same museum collection. A paleontologist named Vasily Mita found them both, collected them both, preserved them both, without initially understanding what he possessed. The significance remains unrealized. These bones have not finished speaking because they have not yet been formally examined. The second skeleton, if it truly is a fetus, carries information about reproduction in the deep sea, about how air-breathing predators managed pregnancy in an environment of crushing pressure and absolute darkness. It could reveal the size of developing young, the length of gestation periods, the investment a mother made in her offspring. It could answer questions about population dynamics, about whether calves were born singly or in groups, about whether mothers provided care in the depths or only at the surface. The science remains incomplete. The specimen designated MCHEIOPM, one continues to yield secrets slowly across decades of study. 3 papers have already been published describing different aspects of the same skeleton. The skull was hidden for 7 years before recognition. The full implications of the body's adaptations took years to unfold. The second shape in the rock may require another paper, another detailed examination, another phase of understanding before its story is fully told. This is the nature of paleontological discovery, not a moment of complete revelation, but a slow unfolding across time. A fossil does not announce its meaning all at once. Understanding accumulates through patience, through repeated examination, through willingness to return to the same specimen again and again. The bones have more to say. The rock holds details not yet extracted. The second shape waits for a researcher patient enough to listen, prepared to spend years understanding what it means to be a developing animal, never born, preserved forever in stone, alongside the mother it would never know. Science builds its understanding through aggregation. Paleontologists prefer populations, ranges, averages calculated from multiple specimens that reveal patterns and variation. A single skeleton, no matter how complete, lacks the context that comparative data provides. Yet the fossil record fundamentally contradicts this preference. Every fossil is an individual, preserved at a single moment, never again to be repeated. Abyssosaurus exemplifies this paradox. Extraordinary information contained in one life, one death, one set of bones. This animal was not special in any inherent sense. It was not larger than its peers, not more intelligent, not more successful at reproduction or survival than others of its kind. It was special only in death, only in the specific circumstances that followed the cessation of its existence. Most animals that ever lived left no trace. They died in places where decomposition consumed them entirely. Scavengers dispersed their bones. Geological processes buried and destroyed what remained. Millions of lives, across millions of years, vanished without leaving any record that they had ever existed. The ones that became fossils succeeded through accidents of geography and time. They died in locations where sediment could bury them rapidly, protecting them from scavengers and decay. They came to rest in rock that formed under conditions that preserved bone structure. They avoided subduction, avoided erosion that would have exposed and then destroyed them, avoided every geological catastrophe that could have erased them. They persisted through 130 million years of planetary change. They remained in locations that were not developed, not mined, not paved over before someone recognized their value. Abyssosaurus beat those odds exactly once. A single animal died in sediment that would become limestone in a location that remained undisturbed long enough to preserve it, in a region that had never been so transformed by human activity that paleontology became impossible. Had the animal died 50 miles away in sediment that would have been subducted, it would have vanished into the Earth's mantle, leaving no trace. Had it died 1,000 years later, the environment might have shifted in ways that prevented preservation. Had the riverbank where Vasily Mita walked been differently placed, his path might never have crossed the exposed rock that held the skeleton. Every piece of knowledge about Abyssosaurus flows from that improbable preservation. The understanding of deep water plesiosaur ecology, of convergent evolution with sperm whales, of specialization and extinction, of the Cretaceous Russian seas, all of it exists because this one animal's bones survived. Not because the animal was exceptional, but because the rock remembering it was. This is the fundamental truth of paleontology. The past that we know is not the past that happened. We know only what was preserved, only what survived erosion and geological violence, only what was exposed before destruction, only what a scientist eventually looked at and recognized. The creatures that became famous, that shaped our understanding of life's history, were not necessarily the most common, the most important, or the most successful in their time. They were the lucky ones. Abyssosaurus was lucky. That luck, concentrated in a single skeleton in a museum in Russia, is the only reason we know it ever existed at all. Life has descended into the deep multiple times. Not just Abyssosaurus and sperm whales, but elephant seals that dive to depths where pressure exceeds anything they encounter on the surface. Beaked whales that hunt in zones of near total darkness. Penguins that pursue prey in cold water far below where their ancestors hunted. Deep sea fish that evolved from shallow water ancestors, losing color and relying on alternative sensory systems as they sank into realms where light no longer penetrates. Each of these lineages made the same fundamental decision: to pay the biological cost of descent, to invest energy in adaptations that allowed survival in an environment fundamentally hostile to air breathers and surface dwellers. The deep ocean represents the largest habitat on Earth by sheer volume. The bathyal, abyssal, and hadal zones combined contain more living space than all surface environments. For most of evolutionary history, this immense territory remained largely unexploited by air-breathing vertebrates. Gradually, lineage after lineage found ways to enter it, to extract what sustenance the deep offered, to survive in pressure and cold and darkness that would kill their surface-dwelling relatives. What this pattern reveals reaches beyond mere biology into philosophy. Evolution is random in its mechanisms. Genetic drift and mutation generate variation without direction. Yet evolution operates under constraints imposed by physics, by geometry, by the finite number of ways matter can be organized to solve a particular problem. The deep presents the same challenge to every air breather that attempts to enter it: how to build a body that withstands pressure, how to extract oxygen efficiently, how to hunt in darkness, how to manage the energetic cost of regularly ascending to breathe. The solutions that work are few. A body must be dense to sink and stay at depth without constant muscular effort. A body must be efficient to survive on scattered prey in an environment of scarcity. A body must see in minimal light or navigate by alternative senses. A body must manage oxygen with extreme precision, breathing rarely, using stored oxygen with ruthless conservation. These constraints narrow the possible solutions so dramatically that the same answer emerges repeatedly across unrelated lineages and different geological eras. Abyssosaurus found one answer 130 million years ago. It weighted its skeleton, calibrated its metabolism to scarcity, enlarged its eyes to capture bioluminescence, developed a jaw suited to ambush rather than pursuit. Sperm whales found the same answer 23 million years ago. Dense bodies, efficient metabolisms, specialized sensory adaptations, the capacity for extended breath holding. The fundamental strategy is identical, despite the lineages being completely separated across more than 107 million years. This convergence speaks to something profound about how evolution actually works. The deep sea is not merely an environment, it is a kind of problem with shape and structure. Whatever enters that space will be bent towards similar solutions because only those solutions actually work. Evolution is constrained, not random in the sense of exploring infinite possibilities. The answers to how to survive in the abyss are limited. Abyssosaurus and sperm whales found the same answer independently, not because they are related or because one copied the other, but because the deep sea exerts consistent pressure on all air breathers that attempt to inhabit it, bending them inexorably toward the same forms, the same strategies, the same way of being alive in a realm of pressure and darkness. The sea that held Abyssosaurus has vanished. The Tethys arm that covered what is now Russia 130 million years ago exists only as compressed stone, marine limestone, miles below the surface. The family line to which Abyssosaurus belonged has left no descendants. The cryptoclitids faded from the fossil record without surviving into the modern world. The ecosystem that supported Abyssosaurus, with its layered water column of ichthyosaurs and ammonites and plesiosaurs, has been replaced by steppe and forest and the Sura River cutting through land. All of it has vanished into time. What remains tangible is almost nothing. One partial skeleton, one triangular skull with orbits too large for the head that housed them, 3 papers published across 3 decades by a scientist in Chuvashia, whose name most people will never know, Alexander Yu. Berezin spent 30 years with one animal, describing it slowly, refining understanding as new questions emerged. The work required patience, the willingness to examine the same specimen repeatedly, to return to it year after year, to publish incremental findings rather than waiting for complete understanding. The abyss that shaped Abyssosaurus kept its creature in darkness for 130 million years. Pressure and cold and darkness selected for dense bones, for enormous eyes, for a hunting strategy built on patience rather than speed. Those selections, accumulated across millennia of evolution, produced an animal unlike anything that had come before it. Then the abyss released it, allowed it to become stone, allowed it to be found. Vasily V. Mita walked along a riverbank in 1992. He was working sediment exposed by water erosion, looking for fossils in a region not known for paleontological discovery. He found bones arranged in marine limestone. He collected them carefully. He had no way of knowing what he held. The specimen entered a museum collection in Cheboksary, catalogued as MCHEIOPM1, and waited there for recognition. The fossil record is not a chronicle of death. It is a chronicle of what the universe chose to remember. Most of life has vanished without leaving any trace. Billions of creatures lived and died and decomposed, leaving no fossil, no evidence that they had ever existed. The ones that became fossils succeeded through improbable confluence of geology and circumstance, through dying in places where sediment could preserve them, through avoiding every geological catastrophe that could have destroyed them, through persisting long enough for someone to recognize their value. Abyssosaurus made it into that catalog. One animal, one life, one existence spent descending and ascending, hunting and waiting, surviving in a realm that killed most creatures that attempted to enter it. That one life was preserved well enough to be read, to reveal its secrets, to teach what it meant to be a deep-water specialist in the Cretaceous. The abyss is patient. It held this creature. It did not let it go easily. The skull remained hidden for years, overlooked among other bones. But eventually it released what it held, in fragments, across 3 decades of careful work. Now Abyssosaurus exists in human knowledge. The bones have been read. The animal has been recognized. That is what they were waiting for all along.